This is the first in a series of videos about the foundations of quantum mechanics. And today we're going to talk about the measurement problem, which is really at the core of why we even need to talk about the foundations of quantum mechanics in the first place. Because the consequence of the measurement problem is that the standard formulation of quantum mechanics cannot be taken as a serious theory of reality. Which is not to say that it's not useful. It can be useful for computation, but the standard formulation of quantum mechanics is not a complete and accurate representation for what is actually going on around us. Now, thankfully, this is not the end of the story. There are other formulations of quantum mechanics, and we're going to talk about those in the next videos in this series. But for today, we're going to talk about the measurement problem, what it is, and why it's such a big problem for the standard formulation of quantum mechanics. Now, as much as possible, I tried to make today's video as self-contained as I could, so if you don't already have any familiarity with quantum mechanics, you should be able to follow along. I'll start the video by talking about the laws of quantum mechanics, and in fact, I'll introduce just as much as I need to in order for you to understand the measurement problem. If, on the other hand, you are already familiar with the laws of quantum mechanics, I made a much shorter video where I explained the measurement problem without any extra explanations. All right, so let's get started. So let's start by talking about some elements of the standard formulation of quantum mechanics that we need in order to understand the measurement problem. And let's start with a reminder. If I have a classical system of particles and I want to tell you what the state of the system is, I will tell you the positions for each of these particles along with all of their velocities. That determines the state of a classical system. Well, in the standard formulation of quantum mechanics, the state of a quantum system is given by a different object, which is called a wave function, which is usually denoted by psi. And this wave function gives us a probability distribution on the positions of particles. You see, there's one fundamental difference between classical mechanics and quantum mechanics, which is that in quantum mechanics, particles don't actually have a position. Instead, there's a probability distribution on the positions of particles. Now, what I just said doesn't really make sense. If particles don't have a position, what does it mean for there to be a probability distribution on those positions? Well, the idea in the standard formulation of quantum mechanics is that even though particles don't have a position, there is a procedure that I can do. This procedure is called a measurement. And if I do a measurement, what will come out is a value for the positions of the particles that is distributed according to this probability distribution that comes from the wave function. Let's talk about a more concrete example. Let's take a simple setting where we have a single particle, in which case the wave function is just a function of a single position x. This is going to be a complex valued wave function. Okay? Given the wave function, I have a probability distribution on the positions of particles that is given by the absolute value squared of psi of x, suitably normalized. Every probability distribution needs to be normalized. But this is the probability distribution that comes from a wave function for a single particle. Now, for example, let's assume that this probability distribution looks like this bell curve over here. So before I perform a measurement of the position of my particle doesn't have a position. Then I perform a measurement. And what will come out is some value on this x-axis here, chosen at random, distributed according to this normal probability distribution. Another big difference between classical and quantum mechanics is that in quantum mechanics, the state of the system, that is the wave function, has a linear structure. To illustrate what this means, let's look at a simple example. Let's consider a particle, and let's suppose that this particle can be in one of these two states. So either its wave function is this blue curve here, psi L, or its wave function is the red curve here, psi R. Well, the linearity tells us that if the system can be in the state psi L or psi R, then it can also be in the sum state, in the state psi L plus psi R. This is the graph that you would get. Now, in this particular example actually interacts with the notion of measurement in a non-trivial way. Right? So if I suppose that my particle is in this blue state psi L, and suppose that I measured the position of the particle, then what would I find? Well, I would find some position on this axis, But certainly, because psi L is equal to 0 on the right of the axis here, certainly the position that I would find would be on the left. Whereas if I had a particle in the state psi r and I measured its position, I don't know exactly where it's going to end up, but it will certainly be on the right. Let's simplify things a little bit, and instead of asking exactly what the position of the particle is, let's consider a different measurement where instead I'm measuring whether the particle is on the left or whether the particle is on the right. So in this case, if my particle is in the state psi L and I measure whether it's on the left or on the right, then it will come out with 100% probability that the particle is on the left. Whereas if I'm in the state psi r and I measure whether the particle is on the left or on the right, then with 100% probability I will find that the particle is on the right. But now what happens in the state psi L plus psi r? In this state, the wave function is not supported entirely on the left and on the right. In fact, it's equally supported on the left and on the right. So if I measure whether the particle is on the left or on the right, I will find with a 50% probability that it's on the left and a 50% probability that it's on the right. But now, this leads to a non-trivial question, because suppose that I perform this measurement, and suppose that I've found that the particle is on the left. And now I perform the exact same measurement again. Right? So I just measure that the particle is on the left, and then I measure whether the particle is on the left and on the right. Well, the outcome of this second measurement should depend on the first one. If I already just measure that the position of the particle is on the left, and I measure it again, then it should come out that it's on the left. The wave function of this system after the measurement should not be psi L plus psi r. Otherwise, there's a probability that it would be on the right. Instead, the wave function after the measurement should look like this. Should look like something that is entirely supported on the left. So the prescription that we follow in the standard formulation of quantum mechanics is that if I start with a wave function that looks like this, I measure whether the particle is on the left or on the right. Suppose that I measure that the particle is on the left, then what I do is I take the entire right part of the wave function and I ditch it. I set it down to 0. This process is called the collapse of the wave function. And so to summarize what the prescription of the standard formulation of quantum mechanics is, if I start in this state psi L plus psi r and I perform a measurement of whether the particle is on the left or on the right, I will find with a 50% probability that the particle is on the left, in which case I collapse the wave function down to psi L by getting rid of everything that's going on the right. Or with a 50% probability, I will find that the particle is on the right, and I remove whatever is going on the left, and I end up with the wave function psi r. Now, there is an important question that follows from here is, how does this collapse actually happen? In other words, physically, what is causing the change in the wave function from psi L plus psi r to either psi L or psi r? To answer this, let's talk about how wave functions naturally evolve in the standard formulation of quantum mechanics. That is, we're not going to perform any measurements, and I want to know if I just leave a system to its own devices, how does its wave function evolve as a function of time? Well, this evolution of the wave function is given by an equation that is called the quantum wave equation, also called the Schrödinger equation, which I wrote down here. It's somewhat complicated. There's a lot of stuff going on here. But one fundamental property that this quantum wave equation has is that it's linear. So what this means is that if I consider a system and I look at 3 different initial conditions, so let me look at some given time t equals 0. Suppose I consider the initial wave function psi L, this blue one, the initial wave function psi R, this red one, or the sum of the two, right? Psi L plus psi R. And so I start with this system in some state. I let it evolve according to the quantum wave equation. So the state psi L will naturally evolve into some other wave function at time t. The state psi R will naturally evolve into some other wave function at time t. But what the linearity tells me is that the state psi L plus psi R will naturally evolve in the sum of the evolutions of psi L plus psi R. So if I look at some positive time at psi L plus psi R of t, I end up getting psi L of t plus psi R of t. That's what the linearity tells us. So this is saying that any natural evolution that does not involve a measurement of the wave function in the standard formulation of quantum mechanics satisfies this linearity property. So how can we explain the collapse of the wave function during the measurement process? Well, the measurement process is a natural physical process. If I want to measure whether my particle is on the left or on the right, I will approach my system with some kind of detector, which is itself made up of a bunch of quantum particles. I will let the particles in the detector interact with the particles in the system, and the result of this interaction should be the outcome of the measurement. Right, so to understand the collapse of the wave function during the measurement process, it should be enough to understand the quantum wave equation evolution during the measurement process. Right, so the natural hypothesis that one would make is that the collapse of the wave function follows from the natural quantum evolution. The measurement problem says that this idea is wrong, that this cannot be true. So let's see how this works, and let's proceed by contradiction. Let's first assume that there is some quantum wave equation with some parameters that reproduces the collapse of the wave function, and we'll see that there's a contradiction. Because what do we require? We still require that through the measurement, if I started with a particle that's entirely supported on the left, so if I start with psi L, then with 100% probability, I should certainly end up with a wave function that remains psi L. So the wave function psi L through the measurement process stays psi L. Same thing, if the particle is already on the right and I perform the measurement, the wave function should remain unchanged. Psi R through the measurement should remain psi R. So what about psi L plus psi R? Well, the collapse rule that we talked about earlier says that if I start with psi L plus psi R and I measure whether the particle is on the left or on the right, then I will get one of two possibilities. With a 50% chance, the particle will come out on the left and the wave function will become psi L. And with a 50% chance, the particle will be measured to be on the right and its wave function will become psi R. Can this collapse be modeled by a quantum wave evolution? And the answer is no, because the quantum wave evolution is linear, as we discussed earlier. So this means that if I start with the state psi L plus psi R, the evolution of psi L plus psi R should be the evolution of psi L plus the evolution of psi R. But the evolution of psi L is psi L, the evolution of psi R is psi R, so the evolution of psi L plus psi R is psi L plus psi R, not psi L or psi R. So the outcome of the collapse of the wave function is different from the outcome of the evolution of the quantum wave equation, which is our contradiction. That's what the measurement problem is. The measurement problem says that the collapse of the wave function cannot be represented by the natural evolution of a quantum wave function. The conclusion of all of this is that the measurement process is not the product of the interaction of the measurement device with the system being measured. But this is a real problem, because physically, a measurement really is the interaction of the measurement device with the system being measured. In the theory that we talked about today, which is in line with the standard formulation of quantum mechanics, measurement is a metaphysical process, in that it's a process that doesn't just depend on the physical properties of the matter that is in the experiment and around the experiment. And a serious theory of reality cannot have a metaphysical component at its core. So this means that the standard formulation of quantum mechanics is just not a serious theory of reality. In the next video, we're going to take a step back and see where things went wrong, and we're going to talk about several proposed alternative formulations of quantum mechanics that don't suffer from the measurement problem. Thank you so much for watching.